Welcome back. We are going to look at the three-dimensional case today, because last time we proved the general pitching theorem, where we showed that once we have the pitching condition for all time, in the case of positive scalar curvature, then the metric, the solution of Ricci flow, will converge to a spherical space form. So now we look at the case of three dimensions. This is, of course, the case of the original paper of Richard Hamilton in 1982 in JDG. And the pitching estimate that we have to prove, of course, starts from the evolution equation again. And recall that the evolution of Ricci curvature under Ricci flow, so ddt gij is again minus 2rij, is given by, this is what we computed, ddt of the Ricci tensor with lower indices is equal to the Laplacian trace of the second derivatives, of course depending on the metric at time t, and then there was a quadratic term on the right hand side, and this quadratic term is given by the tensor 2 times Riemann I p j q times Ricci tensor pq, and then an extra term rik rkj, the trace of the square of the Ricci tensor itself. Now, of course, because we are in three dimensions, we have the luxury that the Riemann tensor can be expressed completely in terms of the Ricci tensor. Since n equals 3, the biotensor is 0, and we can express the Riemann tensor by writing Ripjq equal to Gij Rpq plus minus Giq Rpj minus Iq Gpj, and then plus Rij times Gpq, and then there's another term coming from the scalar curvature, which is Gij Gpq minus Gip Gqj. And now, if you insert this expression in here, you end up with terms which only depend on the Ricci tensor and the scalar curvature. So it's clear what you're going to get. You get one term, just have to determine the coefficients, and you get that the Qij here, this tensor here, is given by one term which looks like the square of the Riemann tensor, the Ricci tensor, and its coefficient is 6. Then there will be one term where the Ricci tensor is multiplied with the scalar curvature, and the coefficient turned out to be -3. And then there is a scalar term, times the metric, and the only scalars that you can build from the Ricci tensor and the scalar curvature is the square of the scalar curvature, and the coefficient is 1, and the square of the Ricci tensor. So it's this term and multiplied with Gij. Okay? So these are the evolution equations that we get. And now from these evolution equations we want to prove our pinching theorem. Now, to do that, the first thing we have to do is to show that our condition of positive Ricci curvature, that was the key assumption that Hamilton made in the three-dimensional case, that condition is preserved. Now, that condition, of course, Ricci positive, is a condition on the tensor, on all the eigenvalues of the tensor. We want to use the maximum principle, but the classical maximum principle is just a maximum principle for scalar functions. So in order to prove a maximum principle telling us that positive Ricci is preserved, we have to extend our classical maximum principle for scalar functions to a maximum principle for tensors. And that's the next step. We prove a maximum principle for tensors. It goes like this, in its simplest form. Suppose, so theorem, suppose that on MA, if a time-dependent Riemannian metric, a symmetric bilinear form Mij of T satisfies a equation of this type, ddt Mij equals Laplacian of Mij, and this is the Laplacian depending on the metric of time t, plus some vector field uk times the gradient of Mij plus an absolute term Nij, some tensor field Nij, such that the following condition holds. Holds for Nij, where and Nij I assume to be dependent on this will be some expression like the square of Mij or the trace of Mij, so it will depend on the Nij matrix, and it will depend on the metric. Assume that this is a smooth dependence, and the assumption that we make is that if Mij anywhere has a zero eigenvector, then on this zero eigenvector of Mij, Nij is greater or equal to 0. So this is something like when you have a scalar equation, you assume that the term on the right hand side, the absolute term, is greater or equal to 0 whenever your function threatens to become negative. In other words, we want this term to push up whenever the matrix here has a a zero eigenvalue and threatens to become have a negative eigenvalue somewhere. And the conclusion of the theorem is then if we have that Mij is greater or equal to 0 at time t equals 0, meaning that all the eigenvalues of the symmetric matrix everywhere on the manifold at time 0 are non-negative, then Mij of t remains a non-negative bilinear form for all t on the time interval where we consider the solution. Okay, so we start with something that has non-negative eigenvalues, and we show it satisfies this equation. The absolute term never pushes it down. This is the condition on Nij. Then this remains non-negative. Now, for the proof, we want to reduce the proof to the scalar maximum principle, essentially. So, for the proof, consider a slightly changed tensor in order to be able to replace weak inequalities with strong inequalities. We replace Mij by something which is strictly positive at time 0, so we add a little bit epsilon times delta plus t times gij. Then it's clear that since Mij at t equals 0 is greater or equal to 0, this implies that tilde ij at 0 is greater than delta times gi. So all eigenvalues are bigger than delta, and delta is some strictly positive number. Now, in the end, we are going to let delta tend to 0 and epsilon tend to 0, prove the theorem. And it's enough to first prove this on a short time interval of size delta, and then we can repeat it until we reach the whole time interval. Notice that since n depends smoothly on n and g, algebraically, that's our assumption. It follows that our condition where that if Mij tilde has a it follows that we can estimate the difference between n tilde of m tilde and tilde ij, which is n applied to m tilde ij g, satisfies that it is not too far away from n, so we get n tilde ij minus nij is bounded by some constant of n tilde ij minus mij, because of the smooth dependence that we assumed of n on the matrix M, and therefore, so if Nij bi Vj is greater or equal to 0, it implies that n tilde ij, vi, vj on the same vector is at least bigger than y is a constant times delta times epsilon. Because the difference between these two is just delta times epsilon, as long as our time interval is small. Okay, so on a small time interval, our two tensors don't differ too much, so our assumption on nij translates into an almost identical assumption on n tilde ij. Okay, so now we argue by contradiction. So we assume that somewhere in this interval between 0 and delta, the tensor m tilde ij has a zero eigenvalue. So now suppose that for some p naught, t naught, so p naught on the manifold, yeah, maybe I shouldn't have, yeah, well, you can distinguish the m of the manifold from the m of the tensor field, and t naught in 0 delta, and some v in the tangent space we get that n tilde ij vi is equal to 0. So we have a zero eigenvalue. Now, what can we say then at these points? Now, we can extend v by parallel transport into a neighborhood of P naught and then smoothly to all of n, such that the derivative of all components of Vj taken at P naught, T naught is equal to 0. Okay? That's the parallel transport with respect to the metric at time t0, so you can make the derivative in all directions of the vector field at this one point at that moment in time equal to 0. Now, if you then consider the function f, I told you that we want to reduce it to a scalar case, so we consider the function n tilde ij vi vj on Mn cross this interval 0 delta. Now this function, since this is the first time where, so since T naught is the first time n tilde ij hits a 0 eigenvalue, we have that is greater than 0 on Mn cross 0 up to T0. And this implies that the time derivative of f at P0 T0 must be less or equal to 0. It must also mean that the gradient of f at P0 T0 is equal to 0 because it's a minimum on the manifold. 0 is a minimum. And we must have that the Laplacian of f at P0 T0 is greater or equal to 0, again because it is a minimum. So we have these three conditions, and now we do the computation for these terms and relate it to our evolution equation and the assumptions of Mij. So on the other hand, we compute ddt of f. Now, the vi, vj is only extended once at the time t0 as a constant in time vector field on the manifold. So there's the only time derivative we have to take into account is the time derivative of m tilde ij. So we get here the time derivative of m tilde ij times vi vj, and this is of course the time derivative of m, and that's our evolution equation. Plus Nij times right, and then, but in m tilde there was another term. So there was this extra term plus epsilon times Gij. And this is whole thing is multiplied. Right, there's another term. The Gij is also has a time derivative, so we get plus epsilon times delta plus t, but delta t is less than delta, so we estimate this by 2 delta times the time derivative of the metric. Maybe write it like this. Times Gi. And then we can, let me just write it here like that. Let's recap ddt times Gij. That's the evolution equation. We get multiplied times Vi Vj. That's our evolution equation. Now, these things here, we have to relate to the conditions here. So we have our inequality here, and we know that this is less or equal to 0 at this point. Now, on the other hand, we can compute what does the condition on gradient k of f mean? Well, this is gradient k of m tilde ij vi vj. Now, here we get gradient k m tilde ij times vi vj, and then because of symmetry we get 2 times the same term m tilde ij gradient k vi times gradient times vj, and the symmetric term where the derivative falls onto the vj, which is the same because of the symmetry in I and j. But we have done this parallel transport, so at the point d naught, this goes away. So this is the same as gradient k of m tilde ij times vi vj at the point p naught t naught, because of our parallel transport condition. And the gradient of m tilde ij is of course the same as the covariant derivative of mij. Since the extra term is just a multiple of the metric, fixed, a constant times the metric, so the covariant derivative is the same. So this shows us that the second term in our evolution equation is 0. So this implies the term uk gradient k mij vi vj is 0 at p naught t. Okay? Right. Next thing we know is that 0 is less than the Laplacian of f at p naught. So computing now the Laplacian, let's take these terms here, we can take this equation here and differentiate once more with gradient k, so we get the Laplacian of m tilde ij times vi vj, and then we get terms where the gradient falls onto one of these things, so we get twice the gradient of k m tilde ij times this, but then we get also another term like that from there, so we get 4 terms which look like gradient k m tilde ij times gradient k vi times vj. And so this goes here, but then there is one term here where the derivative falls onto this one here, so there's a term plus 2 m tilde ij gradient k vi gradient k vj. And finally there's a term where the derivative falls onto this one. So we get plus 2 m tilde ij times vj times Laplacian of vi. Okay, that's all we get. Now, this term here is the same as the Laplacian of mij applied to vi vj. Again, because the Laplacian of the metric is equal to 0. This term here has a gradient of vi, so this is equal to 0 because of our parallel transport condition. Similarly, this one here is also 0 because of the assumption on the parallel transport. Now in this term, we cannot argue that Laplacian of vi is 0, but we know that vi is a eigenvalue is zero eigenvalue of m tilde ij. So we get the last term to be zero because vi is a zero eigenvalue of mij. So we get the whole thing equal to the Laplacian of mij times vi vj. Now this is the first term in the evolution equation. So with this we conclude that 0 is greater or equal than the Laplacian mij here. And we've just computed that that is greater or equal to 0, so we throw it away. The next term is 0, so we have nij vi vj, and we have plus epsilon times gij vi vj, and we have plus, and this one we estimate from below by minus 2 epsilon delta times a constant, depending on the maximum of the time derivative of the metric. We assume that the metric is of course smooth. So we get this estimate. Now, this one here, by our closeness to n tilde ij, we can estimate by n tilde ij vi vj up to a constant which also had the form epsilon times delta. This comes from the difference between n and n tilde times v squared, of course. And then from here comes our good term plus epsilon times v squared. And from here we get another term which looks like minus constant times epsilon times delta times v squared. And now you see we can now use our condition on n tilde because we are on a zero eigenvalue of n tilde. We can estimate by our assumption this from below by 0, and we are left with v squared multiplied times epsilon times 1 minus a constant times delta. And this gives us, where are we here? 0 is this, right. So this gives a contradiction if delta is sufficiently small. It's a contradiction if delta is less than 1 over c. So with this argument we get that the n tilde is positive on the small time interval, and now we can let epsilon tend to 0 and get the result on 0 delta. Then let epsilon tend to 0, and therefore we get that mij is greater or equal to 0 on 0 delta. But now you can repeat, since the delta only depended on this fixed constant c, depending on the smoothness of g and the smoothness of n, we can repeat this argument. This argument to cover all of 0, 2. And this completes the proof. Right, so this tensor maximum principle is very powerful, but let me make some remarks about it. First thing is, we have essentially thrown away the Laplacian. We were not using the Laplacian and the strict ellipticity of this operator at all. So we just used the weak maximum principle. This is a weak tensor maximum principle, i.e. Laplacian was not fully used. We just used the simplest property of the Laplacian to be non-negative on a scalar function which has a minimum. And if you want to get a strong maximum principle, Hopf-type maximum principle, you have to exploit the Laplacian more strongly. So there is also a stronger version using the Hopf maximum principle. This is, you can find in the Hamilton paper that I provided for the course in the four-manifold case. Four manifolds of positive curvature operator explains the strong versions of this maximum principle. So you can also use it to cover the borderline case. What happens if you just have the Ricci tensor, say non-negative, something like that. In the same paper, it's also shown that the whole maximum principle can be extended beyond the scope of just bilinear forms. A more general maximum principle is valid for equations in tensor bundles of the form where some section of the bundle phi satisfies an equation like ddt phi equals Laplace phi is still with the Laplacian with respect to the underlying Riemannian metric, plus some reaction term Q of phi. And then there's a general principle that if, so meta principle, or general theorem, say again in the four-manifold paper above, that if there is a convex set, if for some convex and invariant under parallel transport in the fibers of this bundle, subset K, the ODE ddt phi equals Q phi preserves K. In other words, if the solution of the ODE system, starting from some point inside the convex set, never leaves the convex set, which happens when the ODE points inside on the boundary of this convex set, then the solution of the PDE will never leave K. Of the PDE star will never leave K if the initial data were inside K. So in our case, the convex set K would just be the positive cone of all positive symmetric matrices. And in our case, we have just to show that the ODE system never leaves the boundary of the positive cone. The boundary of the positive cone in the class of symmetric bilinear forms was, of course, given by those tensors that have zero eigenvalues. So we have to show that the ODE doesn't leave the cone. We have to show that on those vectors phi that have a zero eigenvalue, the ODE pushes you back inside, and that was exactly the condition on the right-hand side, the Nij, that at a zero eigenvector of Mij, it's non-negative, so the ODE doesn't leave the positive cone, and then this general principle gives you that the solution stays in the positive cone, which in that case means inside the class of positive matrices. So that's a generalization, very useful, and you also have a strong maximum principle for this setting. Now the third comment is that this cannot be easily extended to other elliptic operators. So it's really important that you have the Laplacian here, because the Laplacian has an invariance under the orthogonal group that makes sure that the diffusion speed is the same in all directions. And that is crucial for the proof of this general principle. It was crucial for our proof. So Laplacian being diagonal with the same diffusion speed in all directions is crucial here. It's well known in chemistry, in the theory of reaction diffusion equations, that if you have two components mixing, giving you a reaction diffusion system, and one has a faster diffusion speed than the other component, then you don't have such a general principle where all convex sets are preserved. There's maybe still some maximum principles, say some quadrilateral regions are preserved, but you don't have such a strong general principle that anything that is preserved by the ODE is also preserved by the PDE. Okay? Only the Laplacian has some of this beautiful property. Now one case where we also have the Laplacian is mean curvature flow, and I'll make a comment on that a little bit later. So now, let's apply this theorem to Ricci flow. So, we had shown in the case of Ricci flow that our case, we prove proposition. First, if n equals 3 and Ricci greater equal to 0 is true for t equals 0, then Ricci flow preserves it. So positive Ricci curvature is preserved. And also, secondly, this is all assuming, everything I say here is assuming compact manifolds. Otherwise I couldn't have assumed there is a first minimum time when zero eigenvalue is attained. Right? So we are in the compact set. So secondly, if the Ricci curvature is strictly positive, then because of compactness, we get some epsilon, that it's bigger than 0. All eigenvalues are strictly bigger than 0. So if the Ricci curvature is bigger than some epsilon times the scalar curvature times the metric, which means that all principal curvatures are bigger than epsilon times the trace for all I. All eigenvalues of the Ricci tensor are bigger than epsilon times the trace for some epsilon greater than 0, ft equals 0. Then this is preserved with the same epsilon. For all time. Okay? That's the theorem we can prove. So in other words, if you have positive Ricci curvature, you stay in the right class. If you have uniformly positive Ricci curvature, then it's preserved with the same uniformity, epsilon. Notice that it's crucial to put R here, the trace, because otherwise, if you just have a constant epsilon, that would also be true actually, you could prove it, but it's not useful because you need the two sides to have the same scale. We know how important it is to have the scaling invariance. And here, only if the R is here as a factor, then these two sides scale exactly the same way, as you can easily see here also. Now, the proof of 1, well, we had ddt of Rij was equal to Laplacian of Rij, and the extra terms we had was minus 6 Rik Rkj and my plus 3R Rij and plus 2 Ricci squared times Gij minus 2 scalar curvature squared times Gij. So now, so this whole thing here is therefore the Nij. And we have to check that Nij is non-negative if Rij has a zero eigenvalue. So suppose Rij Vi is equal to 0. Now, without loss of generality, we may assume that V is just the first direction. And we can also assume, without loss of generality, that we have rotated the coordinate system, that the other directions give make the tensor Rij diagonal. So we can assume that at this one point, at T0, T0, we can always achieve this as one point by choosing our coordinate system. And then we would have, of course, lambda 1 equal to 0. And then we just have to check now if this tensor is diagonal by looking at this sphere, all Nij is diagonal. Nij is then diagonal also. So we have to just show that N11 is greater or equal to 0 as well. Now, what is N11? Now, N11 is here, this is the square of the second fundamental form. So, in the direction of E1, this will be just minus 6 lambda 1 squared, which is of course 0. And the next term will be plus 3r times lambda 1. And then we have 2 times Ricci squared minus 2 times the scalar curvature squared. And now the first 2 terms are 0 because lambda 1 is 0. So we just have to take this thing here. So this is 2 times, and from the first term we get lambda 2 squared plus lambda 3 squared. And from the other term here we get minus lambda 2 plus lambda 3 squared. And now this is equal to 2 times, and then I get here something is not quite right. Let me see. 2 times. Yeah, there was a mistake somewhere. Namely here. This is minus 2 Ricci squared. This is too bad. There's only 1 here. There's not a minus 2, there's just a minus 1. And then I get here 2 times the first one, 2 times lambda 3 squared, and only 1 times this guy. And what's left over is, so subtracting this from this, I'm left over with 1 lambda 2 squared and another lambda 3 squared. And then I have minus 2 lambda 2 lambda 3. And the whole thing is lambda 2 minus lambda 3 squared, which is greater or equal to 0, which is what we wanted to prove. So our maximum principle tells us that non-negative Ricci is preserved. Now, the second inequality is just a little bit more complicated algebraically, but it's the same idea. So, the second inequality, we have to take now our tensor Mij to be Rij minus epsilon r times Gij, and we want to show that this tensor satisfies our tensor maximum principle. And then we compute using the evolution equation of Rij and R to get Laplacian Mij, and then we get the same term that we just had, minus 6 Rik Rkj plus 3R Rij plus 2 Ricci squared Gij minus R squared Gij. This is the evolution coming from here, and then from the evolution of the scalar curvature we get the Laplacian, so this fits in here, but then we get minus 2 epsilon times Ricci squared times Gij, and then don't forget the evolution equation of Gij, which is just our original Ricci flow, so we get 2 epsilon r times r. Okay, that's the right hand side. So now assume that Mij Vi equals 0, and take again V to be E1, Gij equals delta Ij on diagonalize Ricci, and then we have now, if Mij Vi is 0, then we have that lambda 1 is equal to epsilon times r. And then N11, in this case, is just this whole right-hand side. And when you write it down, what you end up with is, minus 6 lambda 1 squared plus 3r lambda 1 and minus r squared plus 2 Ricci squared, which is of course lambda 1 squared plus lambda 2 squared plus lambda 3 squared, and minus 2 epsilon Ricci squared plus 2 epsilon times r times lambda 1. When you work it all out, you just do it. And you use this equation here, the appropriate moment, then I end up with let's write it like this. You end up with lambda 2 minus lambda 3 squared, one intermediate step, plus 2 epsilon times lambda 1 minus lambda 2 times lambda 2 plus lambda 1 minus lambda 3, and then you also get plus lambda 1 times lambda 2 minus lambda 1 and plus lambda 1 times lambda 3 minus lambda 1, and then you replace once more lambda 1 by this equation, and in the end you end up with lambda 2 minus lambda 3 squared times 1 minus epsilon and plus epsilon times lambda 1 times lambda 2 minus lambda 1 plus epsilon lambda 1 times lambda 3 minus lambda 1. But now epsilon is less than 1. Of course you can't prove this with epsilon equal to 1, it would be wrong. The smallest eigenvalue always has to be less than 1/3 of r. So epsilon is somewhere between 0 and 1/3, and then this is positive. And since lambda 1 was the smallest eigenvalue, lambda 2 is bigger than lambda 1, and lambda 3 is bigger than lambda 1. So the whole thing is greater or equal to 0. That's what it's needed to prove this estimate. Okay, so far we have just shown that positive Ricci curvature is preserved, and it is preserved in a uniform way. In the second lecture I show now that we get the pinching estimate.